All right. Eight o'clock. 8:01. Let's get going. We'll get the, let's see, tri beta meeting tonight. No, that's next week. Next week? Been seeing signs if I thought it was this week. Next week, med student from Texas Tech. If you're interested in med school, what it's like to be there, let's try it this time. Mic sounds like static again. Unplugged it, plugged it back in. Let's see if this works. Right. So if you're interested in med school, what it's like to be a med student, come out, hear the talk, bring your questions. I'm sure she will answer them. All right, we've got quiz that's due tomorrow night. Don't forget about that. On Friday, we'll get our exams back. So mostly finished. Should be able to get the grades finished and get them recorded. So let us continue. Predicting population size. This is where we left off. This is where we were going. Try to estimate population size. I bet a lot of this has been repeat material. If you had the biological principles here at ASU, you've had it. I know you've had it. So what we're going to do is we kind of separate our equations that we use. They're similar in that they predict population size and that they account for births and deaths. And we could add in migration if we want to, but we assume that migration is 0, or net migration is 0. But some of the terms change based on this discrete versus continuous and overlapping versus non-overlapping generation distinction. So our discrete generations, when we have our synchronized births, all right, all individuals are born at the same time. And continuous is that you have just continuous births. You have some females are giving birth today, some are giving birth tomorrow, some are giving birth in 2-3 weeks. It's just a continuous type of reproduction. And then we have the overlapping and non-overlapping generations. If we have non-overlapping generations, our population estimate doesn't really need to take into account death rates because all of our adults die at the end of the year. They die before our new cohort starts reproducing. That doesn't occur in overlapping generations, where some of our parents are reproducing while some of their offspring are starting to reproduce. So we're going to start with this discrete non-overlapping generation. All right. Great example are in annual plants. All right, these are the plants that live 1 year. They flower, they set seed, and then they end up dying. And those adults are then replaced. The adults are replaced by all of their offspring. All right, so our population size at our next time point, or in the next generation, is solely determined by the reproductive output of our population. Death doesn't really matter because all of our individuals die. They're all going to be replaced by that next generation. So if all adults die before the new cohort, then the number of deaths that we have is equal to our current population size. They all die. All right? So if we go back to our equation, where we have our population size at that next time point, it's going to be equal to our current population size plus the number of births minus the individuals that died. Well, we just said the number of individuals that die is equal to our population size, our current population size, which means then that our next population size will be how many individuals enter our population. That's the number of individuals that are born into our population. That is our next population size. But then the question is, what is it? How do we calculate that number? Well, that number B, the number of births in our population, is equal to these terms, lambda times n sub t. So lambda is what's called our multiplicative growth rate, or you'll hear me refer to it as the finite rate of growth. The finite rate of growth. Lambda is a factor by which our current population size increases or decreases at each time period. In essence, it's our average number of offspring that are produced per individual. All right, so lambda is kind of giving us this birth rate, right? Not necessarily the number of births, but it's the birth rate. How many individuals, how many offspring each individual in our population is expected to produce. So if we have a rate, then we have to multiply that by our current population size, because we have to account for every individual in our population, and that gives us an estimate of how many births we expect in our population. All right, so our multiplicative growth rate, this lambda times n, tells us how many births are in our population, how many offspring are born into it. All right, got it? So this was our equation. Let's substitute it now to get our actual equation. The population size in the next time period is equal to lambda times n. The finite rate of growth times our current population size. And that is our prediction for the population size next year. But we can make it a little bit more general, so that we're not talking about the next year. We can make it out where we can predict 2 years or 3 years or 5 years or 10 years down the line using this equation. So if this is the equation that for every year, we can convert it to this equation, which is our population size at a specific time point, right, in t time periods, would be equal to our lambda raised to the t times our starting population size. So we would have to know where we start, what's our current size, and then we have to know our lambda to make any prediction in the future. All right, this is our equation. And you could say, well, why don't I need to know this one? Well, if I say what's the population size in the next year, t is equal to 1. We're looking at one time point, one time period forward. So lambda raised to 1 is lambda. We get our equation. So let's calculate this. Here's an example problem. We planted 25 marigolds. Marigolds, flowers, annual flowers. They flower, set seed, they die. For this population, lambda is equal to 1.25. And that's for the seed stock that we have. So the question is, if we start with 25, how many plants will we have in 5 years if we just let them go out and reproduce? So let's work this out. All right, so we start with 25 marigolds. So what variable is 25? That's our starting population size. That's n sub 0. And no. I give you lambda in the problem. Lambda in the problem is 1.25. And I ask you for population size in 5 years. In 5 years is 5 time periods forward. So what we're trying to find is n sub 5. The equation that we'll use, since we know marigolds are annual plants, we're going to use that equation. We have n naught, yep, that's given in the problem. We have lambda, yep, that's given in the problem. Do we have t? Yeah, that's given in the problem. So all we have to do is substitute. So 1.25 raised to the 5th power times 25. So pull out your calculator. 1.25 raised to the 5th power times 25. So in 5 years, we expect to see 76.3 marigolds. $76.3 marigolds. Questions? Good with this? So, annual flowers. Anything that has a discrete, non-overlapping generation. We use this equation. And in the problem, it's going to give you these 3 things. Then, you just have to recognize this is the equation, and sometimes I'll say a finite rate of growth or a multiplicative rate of growth instead of giving it as a lambda here. And that's your clue. If you see lambda, hey, we're only going to have one equation with a lambda, and it's this one. All right? All right. So we have another form when we have discrete generations, but we have overlapping generations. This is a typical situation for life tables. And for life tables, this also applies for some continuous generations, but when we make the life table, we assume that we have discrete generations, just based on our age classes and so forth. So the equations are similar. Similar to this. All right. However, instead of a finite rate of growth, we're going to have a net reproductive rate, which basically means the same thing. Net reproductive rate is the average number of offspring expected per individual in our population. Now remember, I went over life tables, and we're going to see this again. That net reproductive rate is equal to the sum of this LXBX. What was this LXBX term? What did that represent? What did that represent? What did it represent? What is LX? L sub X. LX is survivorship. Yeah, what's BX? There are birth schedules, and then this LXBX is realized reproduction. right? We have to account for survival to that age, all right? And then you have to reproduce. So yeah, our net reproductive rate takes into account this realized reproduction. So just as an example, say we had a life table, and let's say this was a cohort life table. All right, we have 400 antelope. Antelope. Jeez, oh man. 400 antelope. Did that. 400 antelope. All right, so for our life table, we calculated a net reproductive rate of 0.9. We asked, what's our population size in 10 years? So, work that out. All right, so we start with 400. That's our n naught, or n sub 0. Start with 400. I give you net reproductive rate at 0.9. Then I ask, what's our population size in 10 years? So, what value are we looking for? We are looking for n sub 10. Now, before we calculate it, what's our prediction? Do we think it's going to be higher than 400 or less than 400? You think it's going to be higher? Okay. A lot of you think it's going to be higher. Who thinks it's going to be lower? Say no. Maybe? You think it's lower? Why do you think it's going to be lower?
R value.
Because R value is less than 1. Let's check it. So we have net reproductive rate. Our equation for this, same as lambda, but now we're working with a net reproductive rate. So same type of equation. We have everything we need. We got 0.9 raised to the 10 times 400. Those. Pull out my calculator. So 0.9 raised to the 10 times 400. $139.5. 139.5. I could ask, does that make sense? A lot of you thought it was going to go up. Remember our rules with our net reproductive rate. It's scaled at 1. If it's 1, we have complete replacement. Our individuals completely replace themselves in the future, right, in future generations. When R is greater than 1, we have we're more than replacing ourselves, so our population size should increase. Here, each individual is only leaving 0.9 offspring, so they're less than completely replacing themselves, which should then predict a declining population. A declining population. All right, lambda means the same thing. Same types of relationships. If lambda is equal to 1, then each individual is replacing themselves in our population. If it's greater than 1, we're more than replacing ourselves. If it's less than 1, we have incomplete replacement. So just based on the net reproductive rate and the finite rate of growth, we can make predictions about our population increasing or decreasing. So it's always a good thing to do before you start working the problem. Just based on this, I expect it to increase. Or based on this, I expect it. Based on these values, I expect it to decrease. Questions? All right, so lambda versus R naught. So mathematically, there's really no difference. The equations are basically the same. It's just a change in our letters. We've got lambda for one in one equation. We have R naught for the other equation. So the equations are basically the same. All right. they have the same relationships. If lambda or r naught is equal to 1, we have no change. Our population is staying the same. If it's greater than 1, we have population growth. If it's less than 1, we have population decline. They have the same meaning. But conceptually, they do have a difference. This is more of like a conceptual difference, an abstract difference in their meaning. So lambda represents the increase or decrease due to births only, because we use this when we have discrete non-overlapping generations. All of our adults die before their offspring start to reproduce. So the only thing that's going to cause a change in our population will be this births. Either we have more than enough births to replace everyone and increase, or we're not having enough births to maintain our population size, and thus it declines. Our net reproductive rate, though, accounts for both births and deaths, because we have to account for survival to our reproductive age. And we have overlapping generations. Some of our adults are going to be reproducing when their offspring start to reproduce. So mathematically, there's no difference. We have our equations, we use them the same way to make our predictions about population size. The difference really comes into that, the abstract sense. Like, what does it really mean? Lambda is all about the births. Net reproductive rate accounts for births and deaths. Did you finish that? All right, did you get this? So you might be thinking, well, a lot of things don't have this discrete, non-overlapping generation. Annual plants do, that's great. But a lot of this other stuff, we have these births, right? Individuals enter our population, and then some of them will be dying before they reach reproductive maturity. So if we look at an actual population size graph, all right, it's going to look something like this for our discrete generations. You've got jumps from a lower value to a higher value, and then you have gradual declines. Well, what causes these two things? Well, the jump is our birth pulse. Our birth pulse is the reproduction in the population that occurs within that very short amount of time. That's when our reproduction happens. All right, it's discrete. We know when our cohort enters our population. All right, so our birth pulse are these jumps. And then we have gradual decline until the next birth pulse that happens. That represents our natural mortality rate. So individuals do die. They're not going to take part in our reproduction. All right, so you have the birth pulse, then you have gradual death, and then you have reproduction again, and you get another birth pulse, gradual decline, due to mortality, birth pulse, and so forth. So it makes this graph look sawtoothed, jagged. All right. What's our growth rate? What's our net reproductive rate? Well, or lambda. It represents this difference between our points. So we have to pick a point, either the top of our birth pulse or the bottom, right before we reproduce. The difference in those points from here to here, or I have this marked from here to here, that difference represents our net reproductive rate or our lambda. All right, that's our growth. Those are the points that we would use to say what our change in population size would be. Now this is for discrete growth, discrete generations. But through time, evolutionarily, we may start to transition to more of a continuous type growth because perhaps conditions are favorable year round. So what ends up happening is we start taking that time between reproduction and start shrinking it. And as we shrink it, we start getting these birth pulses closer and closer together. And when we do that, we reduce the amount of time where we have our natural mortality. So gradually, as we start shrinking that time between our birth pulses, we start to make our curve appear more smooth, to the point to where we have continuous generations and we have a completely smooth curve. This type of growth curve, when we have continuous generations, is called an exponential growth curve. And we refer to it as exponential growth. Why? Because our population grows exponentially. It'll grow to infinity if we allow it, if other factors allow it. All right, so if we're going to transition from this jagged type of growth curve to a smooth type of growth curve, it's going to change how we calculate our population size in the future. All right, so with our continuous generations, we don't have any clearly defined period between our reproductive events. So in essence, that time, that period of natural mortality is negligible. It's infinitesimally small. All right, so we don't see any birth pulses. We don't see mass die-offs. It's just a smooth population curve. So how do we estimate our growth rates? How do we do that? Well, those of you that have had calculus, maybe pre-calculus, can't remember when we covered these. But our growth represents the slope of our line at any one point. All right, so here's our curve. Make sure I have this. Yeah, here's our curve. We can pick any one point, and at that point, we can make a straight line that touches that curve in a single point. All right, doesn't touch it twice, single point. That point is our tangent point, and it forms a tangent line. The slope of that line represents, the slope of this line, I have it in blue, represents the slope of our population curve at that one point. All right, that slope is change in population size, what we will abbreviate as dn over dt. The change in our population size, dn, for a very small change in our time point. So we use delta n, right, triangle n, to represent change in population size. That works when we have discrete generations. But when we have continuous generations, we don't have a clearly defined time point, so we have to arbitrarily say we're going to look at a very, very small time period, say microseconds. What's our change in population size at that point? So it changes from a delta to one of these lowercase d's. So this represents, this dn over dt is our change in population size for a very small change in our time point. And that is only, that number only applies when our population size is a specific value. As soon as we change our value, it changes our slope. It's going to change our dn dt. So a point for this is that as we increase, as we move up our line and our population size gets larger, the slope of our line gets larger. We have more individuals in our population. We assume those individuals are reproducing. All right. And even if they reproduce at the same rate or they have the same number of offspring, if you have more individuals there, you're going to produce more offspring, which generates a faster population growth. Ready? So our growth rate is really being modeled as an instantaneous change. That's what I meant by our growth rate for a very, very tiny time period. That's an instantaneous change. Right at that point, we're changing at a specific value. All right, so for that, our numbers are going to change. Our equations are going to change. So first, we're going to say, what is that population growth rate at that specific time point? So that dn over dt, all right, it's going to be affected by our population size at that time point and both births and deaths that occur at that time point. Now, instead of looking at actual births and actual deaths, we're going to use rates. So a birth rate or death rate. So we're going to change it from capital letters, which would have represented actual numbers, to lowercase letters. So little b and little d represent per capita birth and death rates. And the per capita just means it's a rate per certain number of individuals. For us, for these equations, it's per one individual. All right, so we're going to account for births and deaths. So we've got a per capita birth rate. So out of all of our individuals, a certain number of them will be reproducing and having a certain number of offspring. And then out of all of our individuals, some of them won't be reproducing, they'll actually be dying because we have a continuous generation, they're overlapping. The difference between our births and deaths, our birth rate and our death rate, gives us this important parameter, R. R is an instantaneous growth rate, and it has two other names. So it's the instantaneous growth rate. We could call it the intrinsic rate of growth. This is also the Malthusian parameter. We'll use intrinsic rate of growth or instantaneous rate of growth. I won't use a Malthusian parameter. This R tells us a potential growth rate of a population based on the differences between our per capita birth and death rates. This is different from lambda and R, big R. So lambda and R naught. All right, now we're looking at rates. All right, little r. R is going to vary between being negative and being positive. Now, in theory, we can go negative infinity to positive infinity, but in reality, we don't ever see that. You're never going to see that. And actually, you're going to rarely see it above 3 or below negative 3. Rarely see those. Usually, our value is going to range between like -1 to 1, and even that's kind of being a little bit generous. But the important thing is that we're centered at 0 for R. So if intrinsic rate of growth is equal to 0, then that means our per capita birth rates equal our per capita death rates. So however many offspring we're expected to have will be offset by the number of individuals we expect to leave our population due to death. So if births and death rates are equal, then we should see no change in our population size. If our intrinsic rate of growth is greater than 0, then that means our birth rate exceeds our death rates. So we're going to have more births, more offspring, than the number of individuals that are leaving our population due to death. If our R naught is below 0, our death rates exceed the birth rates. So now we have more individuals leaving our population due to death than those that are entering our population due to births. All right, so when R is equal to 0, we have population stasis, no change. When R is greater than 0, we have population growth. When R is less than 0, we have population decline. And that sets up a big difference between little r and R naught and lambda. These are centered at 1, all right, because we're talking about average number of offspring per individual. R is rates, refers to per capita rates. Now, I have this here. In all of our problems, I tell you R, but we can go out and calculate. We can actually calculate little r for a population, but we have to do so when our population is small. Why is that? We'll talk about it next week, probably. I don't think we'll get to it on Friday. We might, but we'll talk about it. Why would we measure R when our population is small? What do you think? And I'm saying we're going to try to measure R when we're down here. Why would we do that? So we can calculate its potential growth rate. Keep going. Over time. Why would you say potential? Okay, you expect it to get larger. What's going to happen when our population gets larger? Do we ever expect it to continue going up and up and up and up and up? Why not? You're right, it's potential. Why wouldn't it go to infinity? What cap? What determines our cap? Resources are limited. Right? What kind of resources? What kind of resources could be limiting? Food, that's one. You say environment? Okay. Yeah. I mean, you look at the size of this room. We can't, if we were a population, we can't like reproduce to infinity in this room. One, we don't have like any food, right? And we're limited by space. So this exponential growth, it's theoretical, all right? But as we start increasing our numbers, we start taking into other biological factors. You've got competition to deal with, and competition for all of our limiting resources. You have other regulatory mechanisms that'll start coming into play, which is going to change the shape of the curve. However, when we have this very small population size, our resources are effectively unlimited. We've got unlimited space. We have unlimited resources. We don't expect any sort of intraspecific regulatory factors at work. So yeah, at our small population size, Michael, you're right. This is when we want to do our potential growth, because once we get larger, we have other factors that start to affect our population size. And we will talk about those factors. All right, so population. With this exponential growth, we can estimate change in our population growth at any one size if we know what size we're interested in, that n sub t here, or our population size, and we know our intrinsic rate of growth. Can we also make predictions about population sizes in the future? Yes, we can. The equation is going to be a little bit different. Right? The equations are going to be a little bit different. We still are predicting population size at a certain time in the future. We still have a starting population size. We have to know where we start. But then instead of like lambda or r naught raised to the t, we have e to the r, e to the rt. So you can kind of say e to the r, and then t is also part of that in our exponent. This equation, e, is on our calculator, and on mine, I have to access it from the ln key. So it's shift ln key to get to that e. All right, so let's use this. Examples of exponential growth would include like yeast and bacteria. So who's in microbiology? You're in microbiology, right? Yeah. Micro? Ooh. Are you guys growing bacteria or yeast? You're growing bacteria. So you can go in there. When's your lab? Yeah. Oh, Thursday. So you can go in on Thursday. You can go in tomorrow and say, hey, we can estimate bacterial populations, right? You can demonstrate. Dr. Crable knows that. So let's go through this problem. Yeast exhibit exponential growth with the intrinsic rate of growth of 0.3 cells per hour. Note my labels. All right. Yeast exhibit continuous growth. Yeast exhibit continuous growth. So we don't say, in a generation, this is what they produce. We set up a clearly defined time point and say, okay, within this period of time, this is our growth. So for yeast, R is 0.3 cells per hour. Example number 0.3. So we've got two questions. A, if we start with 10 cells, how many will we have in 10 hours? So in this question, we're asking how many cells do we have in 10 hours? So we are looking for n sub 10. Population size in 10 hours. Well, what do we know? We know R, that's given in the problem, and we know n sub 0. As we said, we started with 10 cells. All right, 10 cells. 10 cells. So we're interested in that. What's our equation? We already said n sub t is equal to n sub 0 e raised to the rt. Rt is in our exponent. So we're looking for n sub 10. We started with 10 cells. Our intrinsic rate of growth is 0.3. And we're at 10 hours. So pull out our calculator. Now this is going to be a little bit trickier. And my recommendation is always to start with our exponent. So I've got e to the x is 0.3 times 10. So e raised to the third power. That equals, I get my number, and then I multiply that by my starting population size. I get 200.9. 200.9 cells. That's what we expect in 10 hours. Second part of the question is if we're at 5,000 yeast cells, we're at 5,000 yeast cells, how fast is our population increasing? Now, do we know that it's increasing? Yeah, we do. R, little r, is greater than 0, so we know our population size is increasing. So what we're asking with this question is, if we have a population size of 5,000, then what is our dn over dt? What is our change in growth rates? Well, dn over dt has the equation R times N. Do we know R? Yeah. Given in our problem. Do we know N? Yeah, it's given in our problem. So it's just substituting. Change in population size. 0.3 times our 5,000. 0.3 times 5,000 is 1,500. So when we have 5,000 yeast cells in our vial, as soon as we hit 5,000, our population growth rate is 1,500 cells. We should be adding 1,500 cells instantaneously. Instantaneously. But that's only at that time point. If we change it to 5,001 cells, we're at 15,003, 15,000.3. If we have 5,002, it goes up. It keeps going up. Because our dN over dt is affected only by R and N, and as our N keeps increasing, so does this dN over dt. We get faster and faster and faster growth. We get this exponential growth. And it'll go to infinity, in theory. All right? All right, so what we're gonna do is stop here. I do have some homework. Practice population growth problems. I'm gonna go look at those. I'm gonna see how they were set up, because I think it also has doubling time on it as well. But I think I've broken the homework down into this part, and then we have the next part, which is our logistic growth equations. So I'll double check that, and I'll tell you, about those. You'll have several days to kind of work through it and get practice. This is going to be on exam 3. All right. So our quiz today, attendance quiz. Let me see here. It's Halloween, so it's Halloween candy. Those are part of our answers. So answers today: Starbursts, Skittles, and M&Ms. Starburst, Skittles, and M&Ms. And off topic, but I 100% believe that there's a difference in cost of production. So when you get those mixed bags, they intentionally give you the stuff that's super cheap to produce, which is usually never the good stuff. All right, so there's 3 answers. That's our attendance quiz. We'll pick this up on Friday. Yep, we'll pick this up on Friday, and then we'll have some practice problems where you can do it on your own. Have a good one.